Hello, math students. Mr. B here again. All right, we're going to do an exponential growth problem today. Here's the story. A town has a population of 1,500 in the year 1980. By the year 2000, the population has grown to 4,300. If the population is growing exponentially, what do you predict the population will be in the year 2040? All right, so we were given some information about the population at a couple times, and we're kind of wondering what's going to happen later. Why don't we do a quick little graph here just to see what the picture looks like. Let's say this horizontal axis is time, and the first year they give us is 1980. Let's also think of that as time 0. And then later, year 2000, which is 20 years later, we know what the population is there too. And let's put our population numbers in. So it starts at 1,500 in 1980, and by the year 2000, it is 4,300. And my drawing's not really to scale, but it'll illustrate what's going on. And we imagine this population is going up exponentially, so it's ramping up. It's not just a flat line. And later on, and again, I'm not to scale here, this is supposed to be the year 2040 when we want the population. How many years is that after 1980? I think that's 60 years after 1980. We have to write our time in terms of years starting from 0. And we want to know what the population is going to be. This is the population on the vertical axis here. Okay, so we're going to figure out what that population is at the year 2040. The master equation for this situation is the amount at time t is given by the starting amount, we'll call that a sub 0, times e to the kt. K is a growth rate, and t is the time. A0 is the starting amount, and a sub t is the amount at any particular time. Well, to start with, the starting amount we're told is 1,500. 1,500. And 20 years later, the amount is 4,300. So I'm plugging some of the data we have into this formula. We don't know the growth rate. That's actually what we're looking for here. Times the time, which is 20 years. In 20 years, the population goes from 1,500 to 4,300. That's how I got these numbers, and I'm putting them into this master formula for exponential growth, which also works for exponential decay, but this is a growth problem. We're going to find that k is a positive number. If it's a negative number, then you have a decay problem. All right, so how are we going to solve for k? Well, the first step might be getting the exponential alone. Let's divide both sides by 1,500. And that will give us just e to the k times 20 on the right. And we can simplify this quantity on the left. First of all, if we divide both sides by 100, that'll give us 43 over 15. 43 is a prime number, so let's just leave that as 43/15. Why don't we write a clean version of what we've got? 43/15 equals e to the k times 20. Now, that k is in the exponent position, and if we know our logarithm properties, the trick here is to take the natural log of both sides. Natural log because the base is e, and you'll see that that does something nice. All right, so natural log of 43/15 on the left, and then on the right side we have natural log of e to the k times 20. The beauty of this is this power is going to come out by the power rule for logarithms and become a coefficient in front. So we'll get k times 20 times log base, log base e, I should write it, ln of e. ln of e. And if you remember another log property which said log base a of a is 1, well, ln is log base e, so we're really getting log base e of e when we're getting ln of e, and that's 1. So this logarithm here is just plain old 1. That's why we use natural log instead of some other base log. All right, so what's the trick now? We've got to get k alone. We're just going to divide both sides by 20, and we'll get k. So k is equal to, and I'm just going to put this into a calculator, get an approximate answer. The exact answer is natural log of 43/15 over 20. But that's a irrational number. It has an infinite number of decimal places. But we want to get a real answer here. We don't want to tell someone some funny answer for the year 2040 in terms of logs and things like that. So we're going to put this in a calculator. What do we get? So give me a few seconds here. 43 divided by 15. And I want to take the log of that and divide it by 20. Sorry, I'm not showing you all this stuff. Hopefully you can do this on your calculator. All right, and I'm going to keep what I call 3 significant figures, which means after the 0 here, I want 3 more non-zero numbers. 7.0527. Okay, well now we can express our population model. We know that the starting amount is 1,500, and we have e to the k, which is now 0.0527 times t. And with this equation, we can predict the population at any time we want. Now you have to be careful. If you go too far out in time, the model probably will break down and not really work very well. But if you don't go too far from the starting time, it should work okay. That is, if you have exponential growth. All right, so we want to know what the amount is when the time, in fact, I'll write it using function notation. We want to know a of 60, right? That's the time when the year is 2040. So a of 60 is 1,500. We're not multiplying here. This is just saying get a at time equals 60. E to the 0.0527 times 60. T is 60. And I'm going to get a number. I'm going to put that in my calculator here. So give me a few seconds here. 0.0527 times 60. That's our base times 1,500. All right. I am getting 35,426.4. Whoops. 0.7. And I want to make a point here about this decimal. There's more decimal places, but I'm just rounding to the nearest tenth. I want to say that what we really should be doing is rounding down to the nearest whole number, because this 427th person hasn't been born yet. All right, so the amount is going to be 35,426. And that's, an approximation. We approximated K. We probably should be approximating this a little bit more, say 35,400 or something along those lines. but this will be good enough for us. All right, hope you had fun with that problem. We'll see you in the next video.